you needed a dramatic reminder that space weather isn't just about pretty auroras, look no further than the headlines from this past November. You probably saw that Blue Origin's New Glenn launch, the one for the NASA Escapade mission, got scrubbed, not just once, but twice. And the issue wasn't rain, it wasn't wind, it was the sun, just spitting out a massive amount of magnetized material.
That clearly was. I mean, it wasn't just rain. It was a highly elevated G4 geomagnetic storm. And that storm was driven by this gargantuan X5.1 class solar flare, which was the strongest of 2025.
Wow.
It forced mission control to just stand down. That single event gave us this stark, real-time demonstration of the critical link between these massive celestial phenomena and our highly sensitive operations right here on Earth, especially when you're trying to launch a multi-million-dollar spacecraft.
Absolutely. So our mission today is to take a deep dive into the sun's dynamic life. We're talking its cycles, the very real and immediate threats it poses to our modern technology. And this is the fascinating part. How these local forces surprisingly shape the search for life across the entire galaxy. So to start, let's unpack the building block of all this solar drama, the coronal mass ejection, or CME. What are we actually seeing when the sun, throws a tantrum?
Well, a coronal mass ejection is the largest single type of solar eruption. You should picture the sun ejecting a massive cloud of plasma and magnetic field mass just out into the solar system. When our telescopes capture it in white light, it often looks like a bright, sort of bulb-like shell surrounding a dark void. It is, simply put, a massive explosion of magnetized solar material heading our way at an incredible speed.
And once that explosion is confirmed, we have to start classifying the activity. I mean, we hear about the solar flares, the CM and X classes, but how do we translate that energy into an actual danger level for you and me here on Earth?
That's where the geomagnetic scales come in. Sunspots and flares, they tell us what's happening on the surface of the sun. But the geomagnetic storm scales tell us the threat level right here. We use something called the K-index, which quantifies the disturbances in Earth's horizontal magnetic field.
And that number, that gives us the G-scale.
Exactly. That number, it's from 0 to 9, is used to derive the NOAA G-scale. And that ranges from G1, which is minor, all the way up to G5, which is extreme. The incident that grounded Blue Origin, that was a severe G4 storm.
The terrifying part, I think, is the timing. I mean, even with our current advanced network of solar observatories, the warning window before one of those massive shock waves hits us it's minuscule.
It really is. We have the DSCO-VR satellite positioned out at the L1 Lagrange point, and that's our early warning system. But the shock wave is traveling so fast, we only get between maybe 15 and 60 minutes of warning time before it impacts Earth's magnetosphere.
15 minutes.
And remember, for missions like the Escapade launch, forecasters need to accurately predict conditions days in advance, not minutes.
So how do scientists improve those long-range forecasts? They can't just look at a few sunspots and guess, can they?
No, they're getting incredibly specific. They're using this extremely detailed metric called the Macintosh sunspot classification. It bins sunspot groups into 60 different categories based on their complexity. 60. And the key discovery here is that they identified a surprisingly efficient group of, troublemakers.
What stands out to you in that data?
This recent analysis showed that 48% of all strong M and X class flares are actually produced by only 8% of all sunspot groups.
Wow, so it's a tiny fraction causing almost half the problems.
Exactly. If you can identify those specific complex subclasses, like the ones they call AI, AKC, and XTU, you can drastically improve your ability to forecast a severe storm days before it happens. It's all about finding that critical 8% that carries all the risk.
That's the perfect example of going from chaos to precision. Okay, so let's widen the lens a bit and look at the sun's approximate 11-year cycle, which alternates between this extreme calm and then upheaval. This long-term dynamic leads us directly to one of the most stunning cosmic paradoxes.
Right, and this is where the sun goes from being a threat to being our necessary shield. Decades of study, particularly across solar cycles 23 and 24, confirmed a consistent inverse relationship between solar activity and the cosmic ray intensity that reaches Earth.
What you're saying that when the sun is having a massive active flare-producing phase, we actually receive fewer galactic cosmic rays?
Exactly. When solar activity increases, more flares, more CMEs, the sun's intensified magnetic activity acts as a much more effective magnetic shield. It literally sweeps away or deflects those high-energy galactic cosmic rays that are coming from deep space. And this temporary cleaning action is known as a Forbush decrease.
Okay, here's the implication that just blows my mind, and I think it will yours too. If that shield is effective, does that mean that astronauts in low Earth orbit, say on the ISS, could they potentially be safer from overall radiation dose during a solar storm than during a quiet solar period?
That is the counterintuitive reality in Leo. You see, galactic cosmic rays are these high-energy particles that penetrate the station's hull very easily. But during a major CME, that blast temporarily sweeps away those dangerous particles. The risk from the solar protons is transient, but the galactic rays are constant.
So yeah,
So yes, temporarily the sun's fury provides protection. Of course, this protection vanishes completely once astronauts leave the shelter of Earth's magnetic field and head deeper into space.
and speaking of what's coming, where are we in the current 11-year cycle, cycle 25? Are the predictions showing more quiet or more chaos?
The simplex projection method predicts that solar cycle 25 will be significantly stronger than the last cycle, cycle 24. And on top of that, the model anticipates a double peak maximum, with the stronger second peak predicted for early 2025. We are undeniably in the active dynamic zone.
And that dynamic zone brings us right back to Earth's critical vulnerabilities. We often forget that these extreme events they're inevitable. A true solar superstorm, a Carrington-class event like the one in 1859, is a matter of when, not if.
The statistics are sobering. The risk of Earth being hit by a storm of that magnitude is estimated at 12% in any given decade. And while the average recurrence interval is around 79 years, these events occur randomly. Our modern, technologically dependent society is far, far more exposed than the telegraph systems of 1859 were.
Let's focus on the biggest electrical danger, geomagnetically induced currents. For listeners, we aren't just talking about a power surge. What is a GIC?
A GIC is essentially a cosmic electrical surge. When that CME hits the magnetosphere, the rapid variations in external currents. They induce these quasi-DC currents through anything on Earth that is grounded and conductive. So power grids, pipelines, railway systems, you can think of it like magnetic energy being converted into a foreign current that suddenly tries to run through your infrastructure.
And that foreign current flowing through grounded networks is particularly devastating for the grid's most vital components.
Correct. The GICs cause high-voltage transformers to magnetically saturate. When a transformer saturates, it consumes excessive reactive power, which destabilizes the entire system. If too many critical transformers trip or overload, it rapidly leads to voltage collapse and potential widespread blackouts. That is the vulnerability engineers fear most.
And the danger is amplified in orbit. What about the millions of satellites, particularly the GPS and communication satellites up at, 36,000 kilometers?
Satellites in geostationary and medium Earth orbit are incredibly vulnerable. They face electrostatic charging, both internally and on the surface, which can cause disruptive electrical discharges. This also accelerates microelectronic upsets, the random errors or memory flips in circuitry, and it shortens the satellite's overall lifetime due to cumulative radiation dose.
And we still face that same timing problem up there, too.
We do. The warning time for a critical charging event is still only 15 to 30 minutes once the CME reaches the L1 point. That gives satellite operators almost no time for real-time mitigation, things like powering down sensitive instruments or repositioning.
Before we move on, we have to mention the risk to people. What about passengers and crew who are airborne during a superstorm?
That's a serious concern. High-altitude air travel exposes individuals to secondary particles from solar and cosmic rays hitting the atmosphere. An extreme event, a G5 storm, could deliver a radiation dose of up to 20 millisieverts.
20? That sounds like a lot.
It is. That's 20 times the annual public dose limit. It implies a serious increased lifetime cancer risk, about 1 in 1,000, for each person exposed during that flight.
That risk is clearly severe enough to warrant official action.
It is. Experts recommend that solar superstorms should be officially classified as radiation emergencies for air passengers and crew. This would mandate formal emergency protocols to manage exposure, redirect flights, and handle the public health concerns that would follow.
If our own sun is acting up like this, it really makes you wonder about the rest of the neighborhood. So let's pivot now to the grander galactic search for life, which brings us to another paradox. The red dwarf problem.
Right. Red dwarfs, or M-type stars, they're the most common stars in the Milky Way, about 85% of them. They live for trillions of years. Logically, they should be the best targets to look for life, but they are terrible neighbors.
Why is that?
Well, planets have to orbit extremely close to them just to stay warm, which causes tidal lock. One side always facing the star, and worse, Many of them are flare stars, capable of doubling their brightness and violence in just a few minutes.
And this stellar variability and all the CMEs that come with it could just blast a planet clean of its atmosphere, right?
Absolutely. Even old settled stars like Barnard's star, which is somewhere between 7 and 12 billion years old, it still flares significantly. And we recently got the first direct proof of how violent these events truly are on other stars.
Tell us about that. The first observed CME on a star other than our sun.
Yes, it was on a red dwarf called STKM 11262. The observed CME was just spectacular. It was moving at 2,400 kilometers per second.
Per second.
To put that in perspective, that single event was faster than 99.95% of all CMEs ever observed from our own sun. That confirms that this intense, violent space weather is standard on these stars, making the prospects for life significantly lower.
So that's the first great paradox. And here's the second. The idea of a galactic habitable zone. Intuition tells us the quiet suburbs, the galaxy's outer regions, would be safer. You're away from the central black hole, away from crowded stars. Yet the outskirts are actually cosmic death traps. Why?
It's because the quiet outskirts are where long gamma-ray bursts, or LGRBs, are most common. These are cataclysmic explosions from massive, short-lived stars, and because the outer galaxy is metal-poor, meaning it has fewer heavy elements, it provides the perfect conditions for the progenitors of these massive explosions.
So the lack of heavy elements out there is the key ingredient for the most lethal cosmic events.
Precisely. LGRBs are incredibly powerful, capable of sterilizing a planet from thousands of light years away. Based on stellar archaeology, our own solar system, which is currently about 8 kiloparsecs from the galactic center, has probably experienced 1 or 2 lethal LGRB events in the last 500 million years. And that incidence rate, it strongly agrees with the hypothesis that a nearby LGRB may have caused the late Ordovician mass extinction event right here on Earth.
So if the solar system is currently nestled in a relatively safe zone, let's look further back, out into cosmic origins. The search for life always starts with the chemistry. We should briefly touch on the purely theoretical first generation of stars, population 3 stars, that started the process of making the heavy elements we depend on.
We found strong circumstantial evidence for these massive theoretical objects in a distant galaxy called CR7, which was 3 times brighter than any distant galaxy previously known. They were the original element creators, paving the way for everything we see today.
And bringing us to modern cosmology, the James Webb Space Telescope is now actively tracing the complex building blocks of life itself in these harsh environments.
It is. JWST recently detected complex organic molecules, or COMs. These are carbon-bearing molecules with more than 6 atoms, and they include chemical precursors to components of RNA. They found them in ice surrounding a massive protostar in the Large Magellanic Cloud, or LMC.
Why is finding these complex organic molecules in the LMC so critical?
Because the LMC is a smaller galaxy, it has a lower abundance of heavy elements and a much stronger ultraviolet radiation field. Those conditions, they closely mimic the environment of the early universe before stars had created all the metals we enjoy today. By understanding how complex chemistry can form under those harsh, metal-poor conditions, we can place limits on how soon life's essential building blocks could have formed after the Big Bang.
What an incredible deep dive. We started with the daily tantrums of our sun, and we ended with the chemical precursors of life billions of years ago. We learned that the sun is simultaneously a powerful destructive threat and our necessary protective shield against the galaxy, that the most common stars in the universe are likely inhospitable fire pits, and the galaxy's quiet suburbs are, counterintuitively, cosmic death traps.
And if we connect all of this to the biggest picture, this whole period of incredible dynamism, the solar storms, the proliferation of life on Earth, the formation of complex molecules, it's all occurring during a very specific window in cosmic time. Based on analysis of star formation rates, we may have already passed what cosmologists call peak star formation in the universe, meaning the long, slow decline has already begun. The universe, over the grand sweep of time, will only get quieter, colder, and emptier from here on out. That should really compel us to recognize just how unique and precious this dynamic, active moment in cosmic history truly is. You are living in the cosmos at its peak.